going to talk about framework agnostic UI tests, and I hope we will have some fun with Pokémons. Okay, so a little bit about me. My name is Shelly. I'm a front-end developer, and I'm a code excellence evangelist. I'm specifically passionate about test-driven development and clean code. I'm a senior principal software engineer in DELL Technologies. So what are we going to talk about today? How to compose implementation and framework agnostic tests in a black box manner. Why? To increase test resilience to implementation and functional changes. How? Using test helpers, assertables, and something we call the driver pattern. It will all be clear in a minute. So I'm going to use Cypress for my demonstration, but the principles that I will demonstrate can be used with any testing framework. So I want to go over two of the pitfalls a development team may encounter in regard of tests. Number one is minor functionality change. So here you can see a partial list of UI integration test suites of a product my team was developing. If we run one of those test suites, you can see every single test starts with user login. And the same goes for all other test suites, because this is how the system works. So now we have a requirement to add mandatory consent to terms and conditions prior to login. So the change is one line of code, but now the login button is disabled until the user checks the checkbox that they read and agreed to the terms and conditions. So what do you think is going to happen to all of those tests? Boom, we have hundreds of failing tests. The other pitfall is maintenance of tests over time. So this is a test from a code repo at DELL, and let's take a look at it together and see what is wrong in this picture. So let's start with the test name. If I see a failing test in a test report that is named check for alerts with actions dropdown, it doesn't help me understand what happened that wasn't as expected. The next issue here is some code duplication. We do not want to repeat ourselves because later if we want to make a change, we only want to change in one place. Another issue here is that we have control flows in our test body. Where we have control flows, it makes it harder for us to understand the test in a glance. If there is a bug hiding here, I have to think and make an effort to find out where this defect may be hiding. This comment here is a code smell. It indicates the test is not clear enough, and we have to explain what is happening. But the biggest sin here is that until this very day, I don't understand what is this test supposed to be testing. I tried to run it, but it's impossible to run it anymore. I will show you in a minute why. But think about having such a test in your project, and now this test starts failing. You come and try to understand, you don't understand, and you are a few days before a delivery. What is most likely going to happen is you will skip this test. Tests don't die, they get skipped. So this is what happened eventually in this repository. The entire stage of the Cypress test was skipped. And take a look at the list of all of these tests on the left. Think about all of the effort that went down the drain. So this is what we're trying to avoid, bad tests. So we want good tests, because writing useful and sustainable tests is crucial in order to avoid such pitfalls. But what are the measures of such good tests? Number one rule is you should treat your test code with the same respect you treat your production code. It is part of your development. But when it comes to test code, we also have three measures we want to comply with: trustworthiness, maintainability, and readability. Trustworthiness means that not only if a test fails, we know something is broken. It means we trust our tests. We don't have flaky tests. We want trustworthy tests and accept the test results with confidence. Non-maintainable tests can ruin our project schedule, or we risk losing the tests when the project is put on a more aggressive schedule. We will simply stop maintaining and fixing failing tests. Oh my God, my voice is breaking. I'm sorry. Readability means not just being able to read a test, but also figure out the problem if the test seems to be wrong. Now, notice that without readability, the other two pillars fall down pretty quickly, because maintaining tests become harder and then we don't trust them anymore. So we want tests that are resilient to change and don't break the minute you blow on them. So let's see just how resilient to change good tests can be. So I will demonstrate how the same functionality implemented using three different frameworks, React, Angular, and Web Components, is tested using the same test code. When developed correctly, our tests need not be affected by implementation details, allowing us to test the UI in a black box manner. So we will be testing a simple application, a Pokédex, Pokémon catalog. We can browse through all Pokémon by clicking on Next and Prev, or we can jump to a specific index. So note the different background colors. Lavender is the lit implementation, dark gray is React implementation, and whatever this is, light green, is Angular implementation. What will we be testing? That Next and Prev buttons should be disabled when we see the first and last Pokémon, respectively, and that the correct Pokémon name, image, and index are displayed. So let's see a simple block diagram of this application. We have a Pokémon catalog component, which uses a Pokémon service, which sends HTTP requests to fetch Pokémon data from the backend server. The Pokémon catalog component is composed from two other components, such as Pokémon image and Pokémon Go. So three components: catalog, image, and Go. Let's run some tests. We will start with end-to-end tests. End-to-end tests are like a helper robot that behaves like a user or a manual QA tester to click around the application and verify that it functions correctly. Let's start with some end-to-end tests on the Angular implementation. What are we testing? Prev button should be disabled when showing the first Pokemon. correct Pokemon name should be displayed, correct Pokemon index should be displayed, and the correct Pokemon image should be displayed. And then the same 3 tests again, once we click on next and once we click on prev, and when we type an index, like here, and click on go, then we see Pikachu. And how about end-to-end testing of the React implementation? What are we testing? Exactly the same things, because the functionality is similar. So our tests are completely oblivious to the implementation, and we only test the output, what the user will see in the browser. And same test suites will run for the web components implementation. Let me just grab a cup of water. Okay, so the test suites look similar. It makes sense. But what about the test code? So let's take a look at this test code. Before each test, we navigate to the home page, and then we wait for the first Pokemon named Babazau to load. In case you are wondering what are all these methods I'm using here, the when, then, get, and other methods, good, stay tuned, it will all be clear soon enough. So then we have tests to assert that prev button is disabled when showing the first Pokemon, that the correct Pokemon index, image, and name are displayed, and that when we're clicking on next twice, we see the third Pokemon. We're navigating to the home page, we are waiting for the Pokemons to load, and then we are verifying that we see the third Pokemon, and then we click once on prev, and we have assertions to see that the second Pokemon is displayed. Things to note here. Each test tests one thing and tests it well. There is no logic, or there are no control flows in the test body. If a test fails, just looking at the test name can give us an indication what went wrong. So which framework is this test code testing? All 3 frameworks. Same test code, runs on Angular, React, and web components. So I'm moving to integration tests. Front-end integration tests refer to running the front-end application while mocking the server responses. So every outgoing HTTP request is being intercepted and a mock response is being returned. This way we can test our front-end without a backend server. So let's run some integration tests. What are we testing? That prev and next buttons are disabled when showing the first or last Pokemon. The correct Pokemon image is displayed, and that when we are fetching a Pokemon by index, an outgoing HTTP request with the correct index is fired. So why didn't we have a test asserting that next button is disabled when showing the last Pokemon in the end-to-end test suite is showing? Because there are almost 2,000 Pokemons, and we don't want to have a test clicking next 2,000 times. So it is easier for us to simulate such a situation or a use case when we, instead of using the actual backend server, we are mocking the responses. So in this integration test, we are pretending there is only one Pokemon in the entire catalog. I will show the code momentarily and you will see. So obviously the same test suites will run for the Angular implementation, exactly same logic, mocking the same responses. And if I switch to the web components lit implementation, also the same test suites. But now let's take a look at the test code. So you can see we are mocking the backend server response, which we will not be doing during an end-to-end test. This way, it enables us to test how the next button behaves when we are showing the last Pokemon. So before each test, we're preparing a response from the backend, and we are, before each test, setting the response to be this Pokemon list that we have created with a single Pokemon. So to get this same result in the end-to-end test, we would have to click on next 1,200 times, or to know the exact number of the last Pokemon. So before each test, we are setting the preconditions of the test. We are intercepting and mocking the response. We are also intercepting and mocking the image, because even rendering an image in the front end, in the browser, actually sends an HTTP request to fetch the image. Then we are navigating, to the home page, and then we are waiting for all the calls to get the responses. And then we have a test to make sure that the next button is disabled, prev button is disabled, that we're showing the correct image, and that if we type an index and click on go, an outgoing HTTP request is fired with the correct index. Note how the test code is phrased like an acceptance criteria. Given some precondition, when something takes place, then we expect the expected result then the actual result should expected result. So even a non-developer can read and understand this test code. This is the level of readability we require on our tests, from our tests. So this is the given, when, and then. Now we're moving on to the Holy Grail. Unit testing, or in our case, as we're working on a components library, a component test. So when testing a UI component in isolation, it is referred to as component tests. So a word, before I will deep dive into it, about test doubles. So spies and stubs are known as test doubles. Similar to how stunt doubles do the dangerous work in the movies, we use test doubles to replace troublemakers and make tests easier to write, because we want to test the component in isolation. It means that the only production code running during the test is the code of the unit under test. All the rest of the production code should be mocked. So no real services, no real anything, any dependencies should be mocked. Okay? So we are using stubs as replacements for actual method that can be manipulated to return the values we want them to return during the test. So these are stubs. Spies spy on functions and can later be interrogated to verify that method that should have been called during the test were actually called. So we are using in this demonstration a package called TS Stubber. It's an open source, lightweight, lazy stubber, meaning methods are stubbed only when called, saving the need to create stubs for every method of the mocked class. TSTubber is generic, so you can choose the mocking framework you wish to use. For example, you can use Jest or Sign-On. Mocked classes constructor is not being called, so there are no side effects during the tests. For example, some services may open a connection to a database or something like this. All of this is being avoided during the component tests. So let's run some component tests. These are the component tests of the Pokémon catalog component. Try not to blink because those run much faster than end-to-end and integration tests, of course. Same test for the Angular Pokémon catalog component. And the same test for the React Pokémon catalog component. So is it the same test code? Almost. As the component has to be mounted at the beginning of each test, each framework mounts it a little bit differently, but that is the only difference. So in our components library, our test code looks exactly the same as we have a generic class to render, and we're using environment variables to make a decision whether we should render a React component or a lead component. But here, to make it more understandable, I am showing the differences between the component tests of the React implementation and the lead implementation. And same goes for the differences between React and Angular. The test code is exactly the same. The only difference is how we render the component. So what's my secret? How am I pulling this off? I'm using helpers, assertable, and test drivers. So let's start with test helpers. Test helpers help our tests to be as decoupled as possible from the testing framework, so that if someday in the future I want to move from Cypress to Playwright, all I will have to do is implement a Playwright helper or test helper for the new testing framework, and all of our tests will still work. Test helpers are designed to decouple our test code from the testing frameworks. Each test helper, every test helper, exposes 3 public properties: given, when, and get, wrapping most useful commands so our tests are as decoupled as possible from our testing framework. Helpers also steer us in the right direction in terms of test readability, because we are forced to use the given, when, get terms in our tests. So as I mentioned before, in this demo, I'm using a Cypress helper designed to be used in any testing level and holds common methods used in Cypress tests. I'm also using the Cypress component helper, which are not framework agnostic, only to be used in component tests to mount the component before the test is carried out. So testers have given, when, get methods. In the given section, we have method for setting preconditions like preparing stubs, intercepting or preparing mock responses. In the when section, we have methods of events that take place during the test, like click, hover, drag and drop, anything a user might do. And in the get section, we have getter methods to interrogate or investigate the DOM, so we can focus on the outcome, what the user sees. What would an implementation of such a helper look like? For example, if we focus on the check and uncheck method in the Cypress test helper, it's simply wrappers of Cypress commands. We are getting the element, selecting the element in the DOM, and then checking or unchecking. A helper is very easy to be implemented. Moving on to the assertable class. The assertable class wraps a subject we wish to assert something about. For example, we wish to assert that an element is disabled. Assertable wraps Cypress chainable so that our tests are as decoupled as possible from Cypress. And by using the assertable class in our tests, we can use the same assertions in our tests regardless of the testing framework we use. All we need to do if we wish to replace Cypress with another testing framework and keep our tests is to replace the implementation of the assertable with an assertable class wrapping the assertions of the new testing framework. The cool thing about assertables is you can also add assertions of your own by extending the assertable class. Here is an example from an open source project of OpenGL maps of adding an assertion that asserts that the subject is included in a style stored in the local storage. So no testing framework will have these assertions for you. You can add your own project-specific assertions by extending the assertable class. And now, the final part of this formula, driver pattern. Driver pattern is similar to page object model, if you're familiar with those. It basically means that we have an additional class which is responsible for bridging the gap between our test code and our component. It will help our tests to be unaware of the inner works of the component. So if we change the way we implement it without changing the functionality, our tests will not be impacted. In addition, if we change something in the component which does cause tests to fail, we will just have to amend the driver and the test will just pass again when the same logic works. If you recall the first pitfall we went over at the beginning, all we have to do is change the login method in the driver and all the tests will be green again. I will show it at the end of this talk. So every driver exposes 3 public properties, given, when, and get. The given property, just like helper, holds methods which will allow us to set the preconditions before something takes place. This is a classic place to have methods which will set the inputs which we are going to be passed down to our component. The when property holds methods of events which will take place, like render, click, hover, anything like that. And the get property holds methods which will give our test access to the output of the component in a black box fashion. So let's take a look at an example. The Pokémon image component displays a GIF image. Unless there is an error, then it shows the fallback PNG image. So what test will we have for such a component? we will have one test asserting that a GIF is displayed given there is no error. So given some Pokemon index and given mock image response, valid response, when we render the component, then the background image should end with Pokemon index.gif. Note how the test code is phrased exactly like I'm saying it. Even a non-developer can understand what's going on here. And we will have another test asserting that the fallback image is displayed given the GIF image is not found. So, given missing GIF image, we get 404 error. When we render the component, then the fallback image should be displayed. Also note, consider how readable the test is and the test name. Now, what will a test driver for such a component look like? So as mentioned before, in order to mount the component, we need to use a component helper. So here I'm creating a lit component helper. For other frameworks, I will create another component helper. The rest of the code is exactly the same. Note how in the given section we have method to set preconditions, but all of the implementation of these methods are using the helper. So we're creating layers of abstraction. The helper wraps Cypress method, the driver wraps or uses a helper to implement the required methods. Anyone, given an example, can write such drivers. It's simple once you get used to it. So the driver uses helper functions to implement the method required to drive the test. Theoretically, if we switch to another testing framework, we will just replace the test helper and the driver will be similar to its current implementation. In the get section, we have methods to investigate the output. So if we're rendering another component, we're just changing the way we mount it, but the rest of the code is the same. But the coolest thing about test drivers is that they can be composed to drive the test of a component which is composed of subcomponents. This way, test drivers can be used as building blocks to compose more and more elaborated test drivers. In our example, the Pokémon catalog driver will hold a Pokémon image driver and expose its methods. We do not wish to repeat ourselves, and we do not want to implement again a method that we already implemented to get the Pokemon background image, right? We already implemented this in the Pokemon image driver. So our Pokemon catalog driver will contain a Pokemon image driver and will expose the given, when, and get methods. What will it? And we can eventually create a driver for an entire page in our application made of many components. And we can also create a driver for the entire application. So let's take a look at the code. This is the Pokemon catalog driver, and it consists a Pokemon image driver. So we are creating the driver and we are exposing the subcomponent methods like so. I've already implemented a method to get the image source of the Pokemon image. I do not wish to repeat myself. This way, if there is a change, I only have to make it in one place. So the containing component driver exposes the method of the inner component driver. And this is what it looks like in the test code. We are accessing the get section of the Pokemon catalog driver, the image driver inside it, and the picture source. So it also helps us understand the path or the scope of where we are within the application. And integration drivers will be composed from all the relevant component drivers. In our case, as this is a simple application, it is only the Pokemon catalog component driver. And in addition, it will contain integration-related methods like intercepting HTTP requests. But in more elaborated applications, it will consist many components drivers. And as shown before, these are the integration tests, and this is where all these methods are coming from, the given, get, and when. So these are framework agnostic tests as promised. And note how most of the driver methods are already implemented in the component driver. You can tell by the path we're using to access the method in the driver. And these are the end-to-end tests, again using the same driver. So we are using the drivers as building blocks, starting from the bottom and building up to create more elaborated test drivers using driver composition. In our projects, developers create those test drivers as part of the development of their components, and they use them in their unit tests and component tests. But later on, when the automation team wants to create end-to-end tests of complicated or complex flows, they have all these testing infrastructures ready to be used out of the box. So they can also compose tests easily and keeping the same style and phrasing of acceptance criteria. Let's take a look at another example. The Pokemon Go component consists of an input field and a button. When the users type an input and click on Go, on submit should be called with the correct index. So what will we want to test? We want to test that Go button is disabled if the input is empty. One second. That Go button becomes enabled once the user types an input. That on submit is called with the correct index when clicking on Go. That non-digit input do not update the input field's value, and that the input field is cleared once clicking on Go. And what kind of methods would we be needing in the driver then? In the given property, we need a method to spy on submit. In the when property, we need methods to type an input and to click on Go. And in the get property, we need methods to get the on submit spy so we can assert that it was called with the correct value, a method to get the input value, and a method to get the Go button so we can assert whether it is disabled or enabled. See how just from going over the driver's code, you can start envisioning the tests and what the test body would look like. And again, just for the rendering, this is not framework agnostic. And what do these tests look like in action? These are the Pokemon Go tests. And And of course, we want to update the Pokemon catalog driver with the Pokemon Go driver because it is also part of the Pokemon catalog. So we create another inner component driver and expose the given, when, and get methods of this driver. So I hope I was able to demonstrate how we create tiny component drivers and then more elaborated component drivers and then eventually integration and end-to-end test drivers. So everything is happy, is well, we are happy, our tests are green, but then someone finds a defect. See how Pokemon 33 Nidorino is active, it's jumping up and down, it's showing a GIF. But if we navigate to a Pokemon that doesn't have a GIF, and then we navigate back to the same Pokemon that we just saw that has a GIF, it is showing the fallback image. So if you recall, not all Pokemons have GIFs. This is why we have the fallback PNG. But some QA finds out that if we navigate to a Pokemon that doesn't have a GIF, when we navigate back to a one that does have a GIF, we get the fallback image. The first thing when we find a defect that we should do is create a bug trap, meaning we should write a test that is failing due to this bug. Only then we will fix the bug. Now note how easy it is for me to compose such a test once we have all those test drivers in place. So it should render Pokemon GIF when we type index 888 and we click on go. We're waiting for the Zacian Pokemon to be loaded, and then we type 33, we click on go, we wait for the Nidorino Pokemon to be uploaded, and we expect that the picture source would be a GIF. This test is of course going to fail, but now that I have a failing test ready, I can fix the defect knowing in confidence that it is actually fixed. So let me circle back to the beginning of this talk for a minute. If you recall, we had hundreds of failing tests, but of course the fix is one line of code. We added to the application driver login method a call to check consent, and all the tests were green again. So to summarize, sustainable and useful tests are trustworthy, maintainable, and readable. The driver pattern enables decoupling of test code and production code, so our tests can be unaware of the implementation details and focus on input. Using test drivers, assertable and helpers, improves our test readability and maintainability. If there is one picture to remember from this talk, it is this picture. The test code uses the test driver, the test and assertable. The test driver uses test helper. Those two are another level of abstraction encapsulating the testing framework. And the test code is unaware of the production code, only the test driver has knowledge of it. Now, those three are open source. The ones that we have to develop, that is proprietary, is the test code, the test driver, and of course, the production code. Now, say you wish to adopt these patterns into your code base, which already has countless tests implemented. How do you start? You start off simple. Whenever you introduce a change, build a driver for the component you change. It does not have to be perfect. Just add the methods you need. Adding one driver at a time, one test at a time, will get you there, slowly but surely. We started implementing those testability infrastructures in our component libraries at DELL about 18 months ago. And at first, there wasn't much, but after a few months, most appliances, products using this component library are adopting these infrastructures. So it may take some time to get used to using test helpers and test drivers, but the best way to have an easy adoption is just to engage in some hands-on practice. So, as I said, it may take some time to get used to it. The best way is to just start. You can find here in this QR code links to the code repo with all the examples, live demos of the Pokémon applications. It will even work from your smartphone. So you can have a Pokémon catalog on your smartphone. Links to an article explaining everything I just went over in more details. And if you wish, you can contact me and we can schedule an online guided workshop to practice test drivers on this Pokemon catalog repository. So, given this is of interest to you, when this session is over, this is where you can get more information. Thank you.